Couple of rules here before we talk about Kirchhoffs laws. One of the hardest things in Kirchhoffs laws is understanding when voltage change is positive or negative. All right, tell me if you can see that or not. Okay. So I obviously have here, I'll put another thing behind this so you can see that a little bit better. So I have two batteries, two resistors, and a switch, etc. And I will connect that here in a second with, I did have another, that'll work perfectly. But just to double check these first, here's a light bulb. So if I put it across here, it's not real bright, but you can see that that battery is working. And this battery, very close to the same amount of current, amount of voltage, and together that's brighter. Okay, no surprise there. If I connect this here. Now, what about the direction of the current flow? I forgot to do that. So let's, I'm going to disconnect this real quickly. I'm going to put the light bulb in. So instead, the current's going to go, I'm saying that the current is going this way, but let's use this handy dandy device known as a diode. Remember, we showed that once. So I'm going to lay that diode right across here, and if it's going the correct direction, then the light will come on. So if I put it this way, the light does not come on. If I lay it this direction, the light comes on. So this, and just to make this obvious, I'm going to take a little piece of blue tape. Put this over on this side of the diode to show that this is the correct direction. So it's going this way. Okay, so we agree that the current is flowing. Come on, get to where you can. And of course, I put it right where it needs to be for to make a circuit. That's brilliant. Okay, so no issue there. So if this is indeed the direction of the current flow, then when I take the light bulb out and I put the resistor in, even though you can't see that it's moving, yeah, I guess we could do this. Let's see if I do this. The light's still on, the current is flowing this direction. All right. Well, now this reads 0 volts, and if I take my from here, I put my negative lead here, and a positive lead here. Notice that reads positive voltage. More positive voltage as I'm across both the batteries. And now the voltage is not changed because it's across a wire. Voltage is decreased. Voltage is down to just about 0 because the diode itself takes a little bit. Okay. Now, if I use these and I go like this, and I'm going to keep them from black to red in the direction of the current. Notice that is positive voltage. Positive voltage in the direction of the current flow. Negative voltage. Negative voltage. Again. If I put this, if we measure the voltage in the direction of the current flow, across a battery it's positive. Across a resistor is negative. In the direction of the current flow. Now, we're about to do something weird, but it's important for our discussion here, and we'll need this light bulb to prove a couple of things here. I've got a third battery to prove that it has the same amount of current, roughly. About the same, yes? However, we're going to put it in backwards. This is going to teach us something important for Kirchhoffs rules. So now, it's going, so note if I do one light bulb, there's one light bulb. Here's two light bulbs. Here's with one light bulb reversed. It's the equivalent of one light bulb, isn't it? Because this one going backwards cancels out one of those. All right, so now let's put this into the big circuit and let's follow Kirchhoffs rules again. So we have our light is on. The bulb, this is not approving. I'm going to take this out. We agree that the current is going this direction, right? Here we go. Across this battery, it's positive. Positive. Negative. Negative. But what across this battery? Current's going this direction. Negative. The current is flowing this way through the battery, and it reads negative. Do we see that? The current here, or the voltage here is positive. What if I go the negative direction of the current? So now I'm going the negative direction of the current. The voltage across the resistor is positive. Voltage across this resistor is positive. Against the current, voltage here is negative. Voltage, negative. And here, positive. Let's talk about what we just did. Make that battery. The battery is not enjoying me right now. For the batteries, the first thing we did is we went around the direction of the current. And we found out from here to here was positive. Positive. Negative. Let's do that again, just to be sure. If I go the direction of the current. Positive, positive, negative. It doesn't matter that the current is going this direction and I went across a battery. All it matters is that from here, that the battery goes positive this way and negative that way, even if you've got the current flowing through the wrong way through the battery. For a resistor, however, it does matter the direction of current flow. The current is flowing this direction. For you guys, counterclockwise. And this is a negative when you're going with the current, and a positive against the current. Go ahead and pause that. We'll go up on the board and draw. We looked at there. So first of all, we have a battery. Call this A and B. Let's say the current is flowing this direction. The voltage from A to B would be, let's just call this EMF, positive EMF. The voltage from B to A would be negative EMF. I guess I didn't need to put the EMF, but it's positive this way, negative this way. On the other side, let's pretend the current is going, well, let me just draw it all again so that no one gets confused by what I'm doing. Here's my battery again, it has an EMF, but I'm forcing current through it. I'm charging the battery. The voltage from A to B is positive. I'm still going that way across the battery. The voltage from B to A is negative. But my current is going the opposite way. I don't care, as you saw in the lab. And if you didn't, go back on this and look at it again. So when I put black here and red there, it reads positive. Black, red, negative. And it doesn't matter the direction of the current. What about for a resistor? Can you see okay over here? So if I have a resistor, and I'll reverse these colors just because why not? There's got to be something out there that this will bother greatly. All the reason to do it. Oh, okay. So if this is my current going that direction, then my voltage from A to B would be negative because you're going across a resistor. That would be IR, wouldn't it? Negative IR. Okay. My voltage from B to A would be positive. Let's just write that to be sure that we know what it is. But if I reverse the current, and you might say, why would you reverse the current? Well, we'll talk about that Kirchhoffs rules, because sometimes you don't know the direction of the currents. You choose currents, and then you make loops. And in those loops, sometimes you'll go the opposite way across a battery. And you have to be able to figure out whether or not that's a positive IR, negative IR, positive EMF, or negative EMF. So now in this case, the current is going that direction. The voltage from A to B, here it was negative. Now it's a positive IR. Why? Because I'm going opposite of the current. Voltage BA is with the current. Now, we do one more thing to show why this is applicable. If I were to take, and this is the example we're going to work that I worked with my class earlier, and I believe it was this. I don't remember what's up here, but that's not super important, but let's just call this R1, R2, R3, V2, and V1. Now, since this one does not have a battery in it, then this one's going to push this way. Would it want to go that way? If you did this, would that big battery push through the little battery? It would go that way. But since I gave it another path, it's going to say, wow, I could push through that wall. Let's say I'm going along and I got the choice to go through a brick wall and a wall made out of paper or out of cardboard or something. I could get through the cardboard, but if you open the door, I'm going through the door. I could choose to go through the cardboard, but I'd rather go through the door. Okay, that's why electricity takes the path of least resistance. And in this case, why go through the cardboard wall if you can go through a door? Okay, it's not a perfect analogy, but that's fine. Go trolls, go! Okay, so let's choose a path. Kirchhoffs rules tell us that around any closed loop, the change of voltage is 0. We've seen that in the lab, yes? So let's choose this right here to be our loop. And we're going to go this way around the loop. We'll call that loop 1. And this is the path that we're walking. Well, let's look at our currents. We're pretty sure that this sucker is going to go this way. So we'll call that current 1. I'm pretty sure that the current's going to go this way, current 2. And these two are going to join up here. And this will be current 3. And we know by the junction rule, they both combine, they've got to come out. You got two freeways coming in, ain't no place to go. We all have seen this in DFW. You come into you got 184 or 114 and 121, they come together, they all got to go through. There's no place to go. So that must be true. This current plus this current must equal that current. All right. Let's look at this loop alone. If I start down here at the negative side of the battery, call that point A, and we'll call that point B. I don't know, I don't care. So my voltage over my sum of all voltages around a closed loop, which actually looks like this, I apologize, summing them all up around a closed loop equals 0. So if I start here, am I going this way? This is the direction of my loop, positive or negative? Positive V1. Now I'm going to go with the current across a resistor.
Negative.
Negative. Okay, then this direction, positive or negative V2?
Negative.
Negative V2. And across this resistor, the current's going that way.
Positive.
I'm going the opposite direction of the current, so positive I2 R2. Now, there's a lot more going on in Kirchhoffs rules, but if you can see what we did in the lab, and you can understand what I just did here, the rest of it's the math part, setting them up, doing simultaneous equations, etc. Stop, please.